Okay, hi, hello. I'm Fadhiilah Balqis. I'm student at UIN Sunan Gunung Jati Bandung, majoring informatics engineering. So here I'm going to be showing how to predict the antimicrobial activity of a set of antimicrobial peptides. Okay, so this is a summary table of all of the peptide features that we can compute using the p-features library, and so you can see here this part here, the custom function for computing each of these peptide features into the same notebook here, and so that might require quite some time. However, if each of us contribute a unique peptide feature, I think we could do that much faster. Okay, so we're going to be importing pandas SPD, and then we're going to be implementing the amino acid composition features here. So from p feature, we're going to be importing the AAC WP, and so the AAC WP here refers to the whole protein or whole peptide, and so you're going to be able to calculate the amino acid composition for the entire protein or the entire peptide, because in p feature there is more than one type of peptide features that you can compute. You could compute the peptide features that are at the end terminal, meaning that it is at the beginning of the peptide sequence, or it will compute the peptide features toward the end of the peptide, and so terminal toward the beginning of the peptide, and C-terminal means that it is the features toward the end of the peptide. But then the WP here means that we're going to be computing the properties for the entire peptide. Okay, so this is for all 19 here, and so if we take into consideration that we're able to compute the N terminal or the C terminal, we're going to be able to have more than 19 different peptide features here, and that could add up to more, but maybe more than 60 or 70. And this show you that in the context of implementing a research project such as this one, we will be having to make lots of decisions that might either simplify the project or make the project much more comprehensive, and that will require more experiments and more calculations. Okay, so simplicity of this tutorial, we're going to be limiting to the entire protein or the entire peptide, and we're only going to be focusing on the amino acid compositions and the peptide composition, and so the amino acid composition here will refer to the percent composition of each of the 20 amino acids that are containing inside the peptide sequence. For instance, if we have a peptide shown above here, for this peptide, I'm going to be counting how many methionine is in. I think it's about 30 amino acids. Let's count it. 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so I think it's 30 amino. So let's implement this and let's have a look at amino acid composition. Alright, and here we go. We have 20 amino acid, and therefore will be 20 columns. Okay, and here we have 37 number of rows, and each row will represent a unique peptide, and so this is the peptide for the positive dataset. Let's do for the positive and the negative dataset. So we're going to be applying the ACC function here that we have just defined, and then we're going to be calculating the amino acid composition for both the positive dataset and also for the negative dataset. And before doing that, let's have a look at the function. So here we're defining a custom function to compute the amino acid composition, and then we're starting to implement this by import the ASC WP function from the pfeatures.p feature. And then here we're defining the custom function, the EF, and then we have ACC, which is the acronym for amino acid composition, and then the input will be the file that we have mentioned on after performing the cd hit, and so the extension of the file will be txt. And so what we do is we're going to be taking the txt from the file name. Here we have the name as trend underscore and underscore cd hit .txt, and also train underscore po underscore cd hit txt, and so we're going to be stripping, and then we're going to be adding ACC at the end. Okay, at the end of the name, so we're essentially remaining the file, and then the output will be here. Here we're using the IAC WP input. Here is the file, and then output is here, the name of the output file. Okay, so essentially the AAC WP function will calculate the amino acid composition by using the input arguments of input. And so this is the input file, and then it will be spitting out, and after we have computed the amino acid composition, we will be reading it into parentheses using ready CCV function, where the output is the input argument, and then we're going to be returning the output at the end of this function. Okay, so running the ACC, the input is the peptide sequence file that has been preprocessed by cd hit, and then it will be generating an output file that has the extension AAC CCV at the end of this prefix of the file name. So the same thing will be for the peptide composition. And let's process the running here, and so we're going to be using the AAC or the DPC in combination with this new custom function here. And so this new custom function is called future calculator and future calc, and so it's going to be taking as input argument 3 here. The first one is the positive dataset, the second is the negative dataset, and then which features do you want to compute. And so it's right here, the positive dataset, the negative dataset. Pause is right here, it's defined here, neg is right here, and this is the negative dataset, and then which feature to calculate. And so we input either AAC or DPC, and so let's actually run AAC because it's much quicker, and I'll leave it to you guys to run the DPC, and this is will be taking. Okay, so here let me start over again. We're defining a positive dataset and the negative dataset by using the name of the peptide sequence and assigning it to positive and negative, and then we define a custom function which will essentially perform the following. So based on the amino acid or the peptide function that if we use IAC, it will be performing the AAC calculation, or if we use DPC defined here, it will be using the DPC calculation here on the positive dataset and also on the negative dataset. Afterwards, we will be getting the features for the positive dataset and the features for the negative dataset. And then we're going to be creating a new column called positive class and negative class. And so the class label here will be first combined together. Okay, so it will essentially be stocked on top of one another and afterwards we're going to be combining it side by side, meaning that the features and the class will then combine side by side in order to get a final data frame, which will contain the peptide features in this example, the amino acid composition followed by the last column, which will be the class label of either being positive or negative. It might be a bit difficult to visualize that, so I'm going to be showing you. Here you see that you have the 20 amino acids followed by the last column, which we have created, and it has two possible values, positive and negative. Okay, so we have already generated the class label positive or negative in this tab right here. Okay, so for the positive data sets, we're generating the positive values here, and for the negative data set, we added the negative values here, and then afterwards we use PD concat to combine the positive and negative into the same column, and so it's using an axis of 0, meaning that it will be stacked on top of one another that you see here. So you see that the positive is on top of the negative, and so this is made possibly. And now that we have positive and negative class labels combined in the same column, we will then be combining using PD concat again, but then this time we're using axis equals to 1, and it means that we're going to be combining the data frames here side by side, and so to the left will be here the 20 columns of the amino acid composition, and then to the right it will be the class label column here, and now we have a data frame of 21. Okay, feel free to run each of this one by one, meaning line by line, so that you will grasp the concept of what is happening as the data is being transformed. Okay, so I want to make note here that feature name here is the same as running this calculation ASC BOS. Okay, it's the same thing. Yes, same thing as running here AAC and the name of the input file. Okay, right. Because we define the name of the input file by pause, so I'm using pause here, or actually we could also do this as well, right? Same thing. Okay, and so it's going to be taking this and then putting it inside here as the input argument. And so for feature name, if we define it to be AAC, it will be AAC here. But if the feature name is defined to be DPC, then this part will be DPC. Okay, let's move forward. And so here pointing note here is that in the next step we're going to be splitting the amino acid features here, the peptide features, the 20 columns into X, and then the class label column here will be the Y, and then we're going to be using this X and Y for SciCat layer model building. And so let's show it here. That's the feature that we have computed earlier. Now we're going to be splitting it into X and Y, and then we're using the drop function to drop the class column, and then we're using the copy function here, and then only the feature class here. So we're taking only the class column and then assigning it to Y, and now we have X and Y. Alright, and then we're coding positive to be 1 and negative to be 0. Now let's have a look at the shape of the X, and we have the combined 2759 right here, and so they are 2759 peptides comprising of both positive and negative in the same data frame. Okay, so now we're going to be removing features that have low variance from the dataset, and then we're assigning it to X2, and let's see how many features have been removed. You can see here that none of the features were removed, but if you were to use the DPC features, there might be some features being removed, and so that is your and here we're going to be splitting the dataset into 80-20 using 0.2, 80, 20, and then using a random stat of 42, and then we're also going to be splitting it using stratify equals to y, meaning that the ratio of the active to inactive will be maintained during the data splitting. And so let me show you the use of the lazy predicts so that we could quickly build more than 30 machine learning algorithms, or more than 30 machine learning models. So actually I've implement again the data split inside the following block of code here. Okay, so installation should take a moment. Okay, so I hope it works, and so let's try running this. Okay, so we haven't defined Matthew's correlation. It's right here, so let's define it here as well. Okay, so it works. So we're importing the necessary libraries right here, and so we split it to dataset again into X and Y, and then we perform the data split into 80-20, and then here we define the CLF using the lazy classifier, because here we're performing a binary classification, and we're going to be using a custom metric called math correlation coefficients, and the matrix correlation will efficiently handle and class imbalance when computing model performance. And afterwards we're going to be fitting the model using the prediction of the training set and also for the testing set. Let's have a look at the performance of the training set. Okay, so it's pretty good. Matthew's correlation is 0.86, and we have it for the random first. Now let's have a look at the task sets. So here it seems that the model task is not working because it's taking several seconds to run. What if I don't run this one? Okay, it seems to work if I run it without the train, and I run only the test. It seems to work. Alright, there you go. It works now. Okay, so probably we might need to run it separately. Okay, so you probably could do something like this. You could run it separately. Okay, so we have the train and we have the test, and now it's working. Okay, so we will process further. Okay, so we're going to be using the tray. Okay, so this is the plot for the accuracy and this is the plot for the Matthews correlation coefficients. So we just have to figure solids processed folder. So we're using the random force classifier and then we're assigning it to RF, and here we define it to have an estimator of. Then we're fitting the model using X train and Y train. And let's make the prediction on the training set and also on the testing set, or the AT. And this is the feature class column, and let's compute the accuracy in the easy way. And we're going to be using the RF score, and so the input argument will be X test and Y test. And so what it would do is it will apply the train RF model to make a prediction data set, and it will compute the accuracy score. Or also, instead of doing here, we could do the manual way where we have to make the prediction. So here, make the prediction, and then we separately store it into two separate variables. One for the train prediction and one for the task prediction using the RF predict input argument X train, saving it here, Y train 3, and then using RF predict on the X task and then setting it separately in Y task. Then we're going to be making use of it here as the input arguments in order to get the accuracy score, and also use the same input argument and compute the Matthews correlation coefficients and others as well, like the confusion matrix as well. Okay, so let's do that. We have the accuracy, and so you can see that you're getting the same result. And let's compute the Matthews correlation here, 0.4. It's actually going to be 7825, and it's going to be inside the big features. And so the model report will be here. We'll go into this file and we double click on it. This is what we get. Okay, so you have a column of precision, recall, F1 score, and supports, and it has the compute separately for the positive and the negative subsets. Okay. Let's calculate RLC. And here we're using the plot RLC curve function, and so a symbol here using the input argument of RF, which is the model, the random force model, and X task, and white test. Okay, so if you want to make it for the training set, we could also do it like here. Change this to train, change this to train. Okay, so that's for the training set, and so we have the area under the curve of 0.99 for the training set, and for the test set we have area under the curve of 0.74 to the same feature importance plots. So this is our data frame. Let's use the Gini index to compute the importance, and let's show it. So that's the Gini score, and let's make a plot. This plot will show the mean decrease in the Gini index. You're going to be seeing the most important feature at the top, and then the last important feature at the bottom. So here we see that the top 5 features that are important are lysine, which is K, D is aspartic acid, E is glutamic acid, AR is lysine, and G is glycine. Okay, so these 5 are performing very well in the model performance. They are the most important 5 features in the random forest model. Okay, that's all for this notebook. So thank you guys for watching. Thank you for your attention. That's all from me. Then I close. Bye.